All right, we can go there. Okay, thank you. Is it done? How can you tell what it is? Right. We might as well get started, I guess. So today we're going to be covering the pancreatic secretion. Ordinarily, we'll be covering that the following week when we're talking about assimilation of nutrients. I have to speak louder.
Just a bit, if you can.
If you can't hear me, let me know. If I'm going too fast, tell me to slow down. Yeah, because now we're entering material from the stomach. Obviously, we're going to be moving it into a small intestine. And we're going to be dependent on two accessory glands, if you will, or accessory organs, the pancreas and the liver, for their proper assimilation of the nutrients we do get into the stomach process. Here we're dealing with the pancreatic circulation. Basically, you can see it looks much like the saliva. Doesn't have myoepithelial cells. But again, the ductal system here responsible for the protein material. And here what we're interested in primarily are the enzymes, pancreatic enzymes. Okay? For the acinar cells, just like in a salad gland, they secrete the protein. You know, enzymes are proteins, right? Okay, the ductal cells are going to secrete bicarb and water. Very similar. It's a little easier to understand, though, we'll see when we get to the transport. But anyway, the ductal fluid is important here for the movement of the material that's generated by the acid, which is the enzyme. So the fluid, bicarb and fluid flushes the ducts into the duodenum down here. Okay, so this goes all the way down. And if you don't have the fluid here, or if it's blood, there's going to be problems. Okay, it's called pancreatitis. We'll get to that at the end. And the other thing that the ductal cells secrete bicarb, pH is alkaline of the juice, and it serves to neutralize. The stomach isn't shown here, but the stomach would be empty, and the potential for acidic colon to be empty, and so the pancreas responds by neutralizing it. Okay, I think we mentioned that before. This is the way this works. This is the bicarbonate secretion we're dealing with. You have HCl here, which is hydrochloric acid, and you'll see as the pancreas secretes primarily sodium bicarb. Doesn't take much to figure this out, does it? Okay, so the two meet, and guess what happens? You're going to get salt and then carbon dioxide and water. So you neutralize any acidic content. Does that make sense? Pretty straightforward. Okay, what does this do? Well, if you're neutralizing the acidic kind, remember the Gollinger-Ellison syndrome, that's a rare syndrome, but it exemplifies the effect of having an acidic solution coming into the duodenum. You can't control very well with your mucosal defenses and your Brunner's gland and the pancreatic bicarb. And so it helps prevent injury due to acid and pepsin. Okay, the two ways, because remember pepsin, pH optimum is low, it's acidic, it's around 2 something. So by secreting pancreatic enzyme, you neutralize the acid and you eliminate pepsin from being active. So two birds with one stone, so to speak. And you can prevent septic ulcer disease. The other thing that's important about pancreatic bicarbonate is that the fluid is alkaline, obviously, and that fits more with the pH optimum of your pancreatic enzyme. Okay, here they're showing trypsin, but chymotrypsin, elastin, and amylase are all within the 7 to 8 range pH optimum. So it's very nice for these enzymes to work. You need a more alkaline environment. You knew you're going to get your transport, but it's a lot easier to understand, okay? It's all on one slide, actually. You got secretion, it's going to be your major stimulant for bicarb, and it's going to be endocrine, hormonal, primarily. Okay, and that's shown right here. There's your secretin interacting with a receptor, adenyl cyclase, and you'll see this again and again. Adenyl cyclase, cyclic AMP, is intimately involved with opening of the CFTR channel. Okay, remember that? That's a chloride channel that can transport bicarb. Matter of fact, if you want to uncover things you can, but mostly we're dealing with chloride here. And what does that do? The chloride comes here and fuels your exchange. And if you're going to secrete bicarb, you have to move similar charged molecule in the opposite direction. And so chloride actually drives this bicarbonate. Okay? That was it. Move bicarb. Where does the bicarb come from? You have to have it come from somewhere, right? You have carbonic anhydrase, a real high level ductal cell of carbonic anhydrase, and that provides bicarb. Also, you move bicarb with this, and well, sodium bicarbonate co-transporter. Now, because it's a co-transporter, you're moving a cation and an anion. Okay, you're trying to maintain electrical neutrality. Basically, you covered everything here, except the housekeeping function here, I call it, because once you're moving bicarb out, what's left over? It's going to be the proton. And acidification is a no-no, just like alkalinization is detrimental to the cell. So is acidification. You got to convert the proton, and you're using an exchange. Again, it's an exchanger. You're moving the proton in exchange for sodium. Those are the things you're going to be dealing with mostly: sodium, chloride, bicarb, proteins, right? Okay, so that takes care of that, I think. And interesting part here is if you measure the pancreatic venous blood, it becomes acidic. Remember, in the stomach, you're putting out a lot of acid, but for all the acid you're putting out, you're also removing bicarb into the venous blood. And here it's the reverse. So whole body acid-base balance is just fine. The pancreas, the venous blood is a little acidic because of this. Okay, you have aquaporin, it's going to move fluid, and that attracts attention to a difference from the salivary gland. I'll cover that in the next slide. But the ductal cells become very permeable to water, and aquaporin is here in the ducts. And so it's going to be isosmotic all the time. Okay, it's going to be normal. Now, I don't know if I covered this enough, but there's paracellular rule. If you're moving chloride or bicarb in one direction, okay, you're going to create a net negative charge, which will allow for the removal. Now, it's an electrical gradient, not a chemical one, but it allows for sodium and potassium, for example, to move passively. When you're moving proton, then passively, it's easy to move an anion, right? Okay, so I just want to attract your attention. So you have everything you need now. Okay, let's take a look at how that works, or the end result of that. As I mentioned, the solution is going to be isotonic. Osmolality just stays the same, but because of the bicarb being exchanged for chloride, and then basically the way you get ductal fluid increases through secretion. Okay, and secretion acts primarily through this system to move bicarb. You know, it's the bicarb chloride exchange mechanism. All right. So now the electrolyte profile is a little easier to understand. Don't ask me why, but studying the salivary gland is not easy. You have multiple glands, you have multiple ducts. So that's bizarre information. But here it's pretty straightforward. Once you stimulate that exchange to the CFTR chloride fueling, then you see that this is basal. It's going to be almost the same. Now it's close to plasma-like, right? All right. So mostly it's going to be sodium chloride. There'll be sodium up here, and there's chloride, sort of, anyway, plasma-like, right? And it's the same thing with bicarb down here, bicarb, a little higher potassium, about the same plasma. So plasma-like, sodium chloride. And this will be primarily driven by things that stimulate the acids, okay, which will be, we'll see, I have here CCK, vagal, and I'll explain it, because most of the effects of CCK are believed to be through that enteric nervous system. I'll talk about that a bit later. Anyway, that's your basal secretion. Now, when secretion comes into play, and the ductal cell starts increasing the flow to wash out the enzyme, it's doing it by moving bicarb into the duct, right? So bicarb is going to go up, and in exchange for what? Chloride. So chloride is going to go down. It's a lot easier to understand. I don't have to start showing you pieces of ducts and showing high flow and low flow. We did with the salivary gland. But basically, it's sort of the same, because even in the salivary gland, the way you move fluid was through bicarb. Through the parasympathetic salivary gland increase. The net result is an alkaline solution, and it's isotonic. Okay? Pretty good. That's pretty easy, right? Compared to that. But see how these transporters are not that difficult anymore once you see them 3 or 4 times. Okay, let's deal with the pancreatic enzymes. And these are, well, amylolytic alpha amylase carbohydrates. The enzymes in the pancreas are very abundant relative to what you're going to be ingesting. Some people estimate 5 to 10 times more enzymes than are required, okay, that are being always added to the duodenum by these secretions. Lipolytic, we're going to take care of lipids, and we'll cover these later, and the proteolytic enzymes. Now, aside from pro-phospholipase A2, which is treated the same way as D, the proteolytic enzymes are all in a form or zymogen form. That's not below it, can't help it. And so they have to be activated, right? And there's a reason they're not activated in the pancreas, because they'll digest the pancreas. They don't care. That's their job, break peptide bond. And we have endopeptidases, trypsinogen, chymotrypsinogen, proelastase, and exopeptidases. And exo, you know, this is carboxypeptidase A and B. It's just different amino acids. But the carboxy tells you it's going to be cutting at the carboxyl end. Okay? If it was an amino peptidase, it'd be cutting from the amino acid. Does that make sense? Nice thing. Anyway, these are in the pancreas, in the brush border to see others. But anyway, you know how endo and exopeptidases work, right? Endo internal bonds are only going to get peptides, you're not going to get amino acids. Exopeptidases, you'll be generating amino acids, and you'll be cutting from the carboxyl end. How are they activated? Okay, you're moving them into the duodenum now, so you have to activate them from the zymogen form. And there's a brush border peptidase called enteropeptidase, and it'll cleave trypsinogen to trypsin. Now that's the key over here. Once trypsin is activated, or active, if you will, the active form, it'll activate all the other ones. More trypsinogen will be converted to trypsin, that comes back, and then all the other peptidases get activated. So it creates a cascade. Remember, like in the stomach, once pepsin became activated, it activated other trypsinogen molecules, right? So it creates this cascade or waterfall effect. you will. The pancreas also secretes, I gotta remember that. The pancreas also secretes something called trypsin inhibitor, and it's secreted at much lower concentration than the pancreatic enzyme. And its main job is to prevent any accidental activation of trypsinogen to trypsin, because once you activate trypsin, you're going to be activating all of them. So that's a safeguard, but there's not enough being secreted on a molar basis that when these enzymes end up in the duodenum, it doesn't inhibit their activity. Once this cascade of activation happens, there's not enough trypsin inhibitor to stop it. Okay, so it's in the pancreas as a safeguard. It has trypsin inhibitor. Now the enteropeptidase story. Some of the textbooks you'll be reading will have enterokinase. We had biochem, right? You know what a kinase does? Phosphorylate. Remember that? This is not phosphorylation. This is hydrolytic cleavage of the peptide bond. So that's why the biochemists renamed it. Okay. But originally, when it was discovered, whoever discovered it called it a kinase, called it enterokinase. So sometimes you'll see that. And if that's the only choice given on some kind of an exam, pick it, because some textbooks haven't changed yet. Most have. Called really an enteropeptidase. You'll see the same problem when we get to digestion of lipid. Triglyceride is rather an old term. And I think we have lipid cuts, right? Is that what you use, lipid cut? Biochem? Yeah. I think it's called triacylglycerol. You probably haven't had lipids yet. No, well, we'll cover a little bit anyway. Okay, enteropeptidase is required to activate it. It's conveniently located in the duodenum and brush water. So now your inactive enzyme is secreted, washed in by bicarbonate water, then activated by this brush water enteropeptidase. The physiologic agonist, I'm going to start emphasizing this because I've been emphasizing the CCK activating sensory neuron. Secretin works as a hormone on the ducts. It goes through circulation, comes back up to the pancreas, and activates the duct. So I have secretin in red, and it promotes multiple arrows. That means that's a major impact, okay? Acetylcholine and CCK working through acetylcholine primarily. We'll get to that in a minute. It'll potentiate. I think it's going to be shown in another slide. But you know, these two, because they're using different pathways, signaling pathways, they potentiate the effects of it. And then the acinine, the major player is going to be acetylcholine. But you're going to need CCK to make it work. Remember that it'll be very similar to the gastrin-histamine axis kind of thing. Okay, and secretin will help, but it's a minor player in terms of the acinar secretion. Okay, and this is what I was talking about. Acetylcholine through CCK will activate the calcium. Whereas secretin, we already mentioned that, works through adenyl cyclase, cyclic AMP, CFTR, chloride, fueling the exchange. But because they're from different families, they can potentiate their effect. I'll attract attention here with the red or the dashed square, and that's this basic. And here what you're showing is carbohydrate meal. Okay. And you're showing amylase output out of pancreas. And the thing to track into is the cycle. It cycles with the MMC. Remember the migrating motility complex? Okay. Every, I don't know, what do they have it here? Roughly every 90 minutes or something, an hour, depending. But every time the phase 3, remember that's the activity front, that's the one with the strongest contractions coming through. Then the sphincter of Oddi. Have you had that yet? Okay, that relaxes and allows juice to enter the duodenum. So you always have some basal pancreatic secretion occurring, and this is the enzyme output. Same thing would be, that's just representative, the same thing. You see, trypsin, chymotrypsin, etc. That's just an example. Now that's a little tricky because Motulin doesn't induce secretion. And then if you cut the vagus, it inhibits these things. So they're thinking it's cholinergic, but it hasn't really worked out. So don't worry about it, except know that there's basal secretion. And they think that hasn't been proven yet, but they think the importance of this is that when the MSC is coming along, any roughage or cells that are, it's helpful to proteolytically digest some of the material as moving it down into the colon. That's what they think is going on. Okay, remember we were going to be dealing with cephalic, gastric, and intestinal secretion, right? It's just a matter of discussion because all of this, you'll be thinking about it. Your stomach's going to be filling and you're going to be starting to empty. All continue. But here you're dealing with, in the green here, cephalic, smell, taste, chewing, that kind of thing. It's going to be vagal, right? And as I mentioned repetitively now, acetylcholine is going to stimulate the acid, right? So mostly you're going to get enzymes, but you'll have some fluid as well, right? You got to wash it in. The problem if you don't deliver. So that's what do they say? 25% of the pancreatic output, but flow-wise, 10% or something like that. Yeah, that's mentioned down here. 10% in. Oh, that's gastric. The gastric phase, the stomach is not interested in chemical. Okay, so rarely here you have taste, you activating sensory neurons and stuff. Taste, smell. Okay, these are chemical signals, but in the stomach, it's all mechanical, pretty much. And there's distension that's going to do it. And remember, distension in the stomach is going to cause a little bit of relaxation in the fungus region, but also distension triggers the vagus to the pancreas. And the pancreas is innervated to the postganglionic neuron present in the pancreas. Postganglionic of the parasympathetic. Okay, it's not the entire nervous system in the pancreas. Remember your autonomic nervous system? I think we sort of reviewed that in the first lecture. It's going to be these neurons that are postganglionic. There, liver, salivary glands. So that's going to relieve acetylcholine. Okay, so your major players here are going to be acetylvagus and acetylcholine. Okay, and some fluid coming out. Now, in the intestinal phase, which is, well, usually it's going to be the most of your response, pancreatic response, both pancreatic and fluid. And a major player here is bicarb output, fluid output. And what we're showing here is duodenal pH and bicarb output and plasma secretin. It's going to be working at the hormone, the receptor for secretin. Duct cell and somewhat on the acid, more on the duct. And you can see that once the pH falls below 5, around 4.5, secretin starts going up, and bicarb secretion by the pancreas is going up. Okay, and as you lower pH, more and more secretin, more bicarb output. It all makes sense in a way, and then it reaches maximum value at around 3, and rarely under normal circumstances anyway, not the value, but rarely it's going to go below 3. Because then you're also lacking on the pancreatic enzyme, non-functional. Doesn't help much if you don't have the enzyme. I mean, if you have them, but they don't work. Okay, that's pretty straight. And this is a little cartoon. I call editorial license to kind of make this up, but it fits more with the literature. And basically, fat is going to be a major player in the intestinal phase, and it's going to work through CCK and acetylcholine. We'll come to that. And this is showing you that, well, it's going to be hydrolytic products of lipid, which is primarily long-chain fatty acid, short-chain fatty acid, not so much, but long-chain fatty acid, next shown here, the major player. I also have lipids in red. Then protein is the next most potent stimulant for cholecystokinin secretion. And then carbohydrates are released, if you will. Okay. Mostly we're dealing here with enzyme output. I could have put enzyme secretion as well here, but this is, you understand what CCK and acetylcholine are going to do, right? Promote enzyme release to deal with lipid, protein, and carbs that you ingest it. It's a matter of potency. And this is the way it sort of works. You have the eye cell and the duodenum, like that. I don't know if people pick on me for that. I don't. I'm not going to worry about whether you know which cell it becomes. But it's going to activate the eye cell, which makes CCK. By the way, most of these enteroendocrine cells secrete one or two different peptides. Okay. But anyway, the major product of the cholecystokinin, it's going to activate sensory neuron. These will be extrinsic sensory neuron. Remember the cartoon I usually draw enteroendocrine cells with? You can have intrinsic, but here you don't have the enteric nervous system. It's all going up. It's a vagal response. It comes back down. And here we're dealing with acetylcholine. And we'll deal with this later, VIP, which is relaxant, and nitric oxide. So you have some of those neurons present as well, postganglionic. Now here, cholecystokinin classic, we consider endocrine functional hormone. And if you're giving some kind of an exam somewhere, and they don't mention the vagal reflex, and they just tell you the hormone cholecystokinin, pick it, because some textbooks still have cholecystokinin working as an endocrine, but it doesn't. A major activator of pancreatic acinar cell is going to be acetylcholine, not cholecystokinin, very low receptor. And here, the CCK receptor on these nerves is CCK1 or CCKA, depending on which textbook you read. And sometimes it's referred to as the enteropancreatic. And we saw this effect of CCK when we were talking about inhibiting gastric motility and then acid secretion as well. Okay. But this is the most important thing. It's the way it works. Now you're going to have some feedback regulation in the duodenum. This is a cute little one. Let's see if I can not get mixed up and try and explain this, but you have ordinarily some, remember that cyclic MMC coming by, we're going to have some basal, secretion of these enzymes, right? Okay, so let's say I showed you amylase, but the same thing we've seen with trypsin and with chymotrypsin and lipase. In other words, I forgot to point that out, but in these granules, you have the entire complex. In other words, it's not like one granule has trypsinogen, another granule has lipase, another granule has your amylase. No, they're all packaged into one. So that's why it's always going to track the same, because every granule has the full complement of enzymes required. Okay, I should have mentioned that earlier, but better late than never, right? Now it's easier to understand. But anyway, you have this protein being secreted. It's called a Cck Releasing Protein. CCKRP. Okay, you don't even have to memorize that. Just remember it's a releasing protein, and it's just secreted, continuously secreted by these particular cells. And ordinarily, during basal secretion, you'll have some trypsin there. And trypsin will inactivate this thing, and so it no longer activates the eye cell. You don't get CCK, you don't get the vagal response, okay? So if the trypsin, if the basal secretion is actually preventing enzyme secretion, what for? You don't have any, you haven't ingested anything, right? But now you'll notice this bar, I'll take it off in the next slide, okay? So now, let's say you ate some meal, you're gonna have protein. Now you got a competition going. This, I'll have to remind you several times when we get to that. Once we're down here and we do it, you know, it's a soup. These enzymes, they don't care who they're attacking. They don't have a brand, okay? They're just hydrolytic. They're gonna, whatever peptide bond they see, they're gonna cut, including your own, well, rough, but activation. But trypsin will eventually they'll degrade each other. Okay, the peptide, right? The protein. So it's like a soup that's going on in there. So what's happening is the trypsin is now becoming preoccupied with the protein you ingest. Okay, which now the trypsin is, the competition is favoring the proteins you ingested, less degradation of this molecule, and you get more and more enzyme secretion, okay? So now when the protein goes down, trypsin turns its attention back to this thing and starts shutting off the protein, the enzyme secretion, but you don't need it anymore. Did I explain that adequately? You're okay with that? Go back and forth, okay? And just think of it as a competition and a mechanism for not wasting the pancreatic enzyme, either basally. If you don't have any protein that you ingested, trypsin is free to inactivate this thing. No enzyme doesn't activate the signaling necessary, right? Once you've eaten something, okay, you promote enzyme secretion for efficient digestion, if you will. And there's plenty of enzymes to take care of everything. Okay, I mentioned this. Now let's just look at the differences in the red and the blue here. These granules, I bring it up here. Okay, I do bring it up. They contain the entire compound. Okay, they have everything. So when they remember this in humans, well, when let's say you switch to a high carb diet, which the reason we have this high carb, low carb, carb diet used to be a favorite with people who were active, athletic, if you will. They went to high carb, and when you measure the enzyme concentration, here we have amylase, the appropriate protein for the high carb, right? You have amylase that they measure. It's much higher when they switch to a diet, but this takes time, days, weeks, maybe longer, and they think it's due to eventually turning on genetic machinery to start making more. So you're going to secrete all your enzymes again, the full complement, okay? But you're just going to have a little bit more amylase than you did before you started a high carb diet. And you'll see the same thing. Yeah. If you go through a high fat diet or switch to a high protein diet, it'll take a long time. And it's a genetic thing, required protein transcription, gene transcription, protein synthesis. It takes a while, but the diet can modulate that. I talk about pancreatitis. This is a slide I picked up from the internet. Google. You can find it yourself. Look, it's a kid's slide or something, kids' health or whatever it is. But it tells the story. Here you have pancreas to the stomach. I like that. Anyway, the pancreas is going to secrete these enzymes, right? We have a little bit of trypsin inhibitor. Now they either go into or somehow you prevent them from entering to do it again. So think about that. They're stimulating the pancreas to secrete, but you're either blocking it, something wrong with the ducts, etc. You're gonna inadvertently activate these enzymes. It's called auto digestion. I think I mentioned it before. But pancreas basically eats itself. Well, that's a crude way of putting it, but it starts causing injury and inflammation. And, anything that ends in itis, we know that's inflammation, right? Gastritis, pancreatitis. Now, so if you block this system, you have a chance. And one is gallstone for the top, pancreatitis, okay? Cystic fibrosis. As a matter of fact, the term cystic fibrosis comes from autopsy, people that died and they found cysts and fibrous material in the pancreas. So they call it disease cystic fibrosis. That's not why the people died. They died from lung issues, but that's where the name came from. And it's due to a lack of CFTR. There's some mucus secreting cells in the ducts. And if you have any sluggish movement, more chance for activation. Okay, so that's a problem. Fibrosis usually don't have pancreatitis. Chemical. Now in the West, this is the major cause for pancreatitis, but here not so much. I think it's illegal, right? So that's not an issue usually in Islamic countries. Mechanical, I know that firsthand. If you touch that pancreas, or it's human or experimental animal, doesn't matter. You touch that pancreas and it swells up. It's very, very fragile organ. You don't appreciate that when you're doing cadaveric dissection. But in the living, as a matter of fact, it's a food in some cultures. Anyway, any surgery, even stomach, something that's really not connected to the pancreas, just touching the pancreas during the surgical procedure can induce an acute pancreatitis. It should resolve and it won't want, but still, that's how sensitive it is. And bariatric, I mentioned here, is a common complication of that. Bariatric surgery are different. Some are gastric, some are, they do something, they bypass ducts and stuff, but it's usually to treat obesity. What they're trying to do is limit your fat intake. And one way is gastric clamp, they make your stomach smaller, or other surgery, okay, to deal with the satiety factors, so that you feel satiated and full earlier than you normally would, and that helps you lose weight. Bariatric surgery. What are the consequences? Diarrhea. I mentioned that, and there's some notes down there. Diarrhea, I think, maybe the reason we always bring that up because a patient, when he has very foul smelling stool, and they attribute it to the bacterial degradation of liquid. Okay. Also, lipase is one of the more sensitive enzymes to proteolytic degradation within the intestine. In other words, trypsin, other enzymes will attack it. You rarely find lipase in the stool. Okay. And then, of course, you're going to malabsorption. You're going to have anything that has to do with lipid soluble material, malabsorption. But you'll also, if you're destroying enough of the pancreas, you'll also be losing the enzyme to digest protein, hydrolyte protein. So everything is really affected. Okay, malnutrition, you can lose weight, but a major clinical sign would be diarrhea, and people will know that. And obviously abdominal discomfort. Okay. Now, you can measure this this, let me see, okay. Some people say you can destroy 90% of your pancreas before you affect the capability of hydrolyzing all the material you inject. In other words, the pancreas supposedly makes 9 to 10 times more enzymes that are required, right? But that's not completely true. There's arguments against that now, the better safe than sorry kind of thing. Once you start losing a major portion of the gland due to, inflammation, fibrotic issue, healing, fibrosis, basically scar tissue. Anyway, you're gonna cause something called pancreatic insufficiency. We'll cover it later when we get into maldigestion and diarrhea. Pancreatic enzyme replacement there. Nice little word, RT, right? That's what they do. Okay, you don't have the enzyme, but we'll give them to you. You take it as a capsule. There's a problem with that here, I think, maybe not. Anyway, this that here they're showing you can't do this in your office for obvious reasons. You're going to have IV. We have synthetic secretion, that's not a problem. And then you have endoscopy, you have to anesthetize the person, okay. And you go down to the duodenum, and then you sample fluid coming into the duodenum from the pancreas, and you collect this fluid over time in response to secretion. Cholecystokinin is not going to give you much of a fluid response, but secretion will on the duct cell. But now they have non-invasive, direct. By direct, they're actually measuring something, right? So here they're actually, instead of, here they're injecting secretin, so it's kind of direct, but it's invasive. Here is indirect, they're measuring the actual enzyme being secreted in the tissue, okay? And they use the last dimension. Lipase is pretty good on, it's going to be destroyed, so they don't usually measure that. Same thing with Trypsin, okay? But elastase right now seems to be the choice, and they have basic amino acids, or lyses they call, enzyme-linked amino acid kits, little kits. And all you have to do is collect. We hope patient compliance is important here. The patient's got to collect stool for 72 hours, but you only need a little bit of stool, but it has to be collected for 72 hours. Some patients don't exactly follow all that. Indirect, the same concept, you just measure fat. Because, as I mentioned, steatorrhea. Steatorrhea, all that means is fat in the stool. It doesn't necessarily mean diarrhea. But usually it will be diarrhea. Okay, I think, is that okay? I think that's straightforward. And have a good day. You got presentations coming up or something, huh? That schedule has been changed almost daily. I hope you people look at that weekly time. Okay. I guess you gotta take a 10. You don't need me.